So in the second part of the lecture, we will be looking at various scheduling policies and pros and cons of each of the scheduling policies. Okay, just to refresh our memory, we know that we have four fundamental goals for any CPU scheduling policy. They're to minimize turnaround time and maximize throughput, and to have a short response time. Finally, this CPU scheduling policy should be fair, which ensures that there is no starvation and no deadlock among processes. Okay. So let's look at the first and most simple policy, which is FIFO or FCFS policy. So it stands for first in, first out, or first come, first serve policy. So this is a simple policy that we saw in lecture 3. So here what happens is the processes are scheduled in the order in which they arrive, and each process will be run to completion unless they are blocked and a process voluntarily yields the CPU. Okay. Until then, the process will be scheduled on the CPU and the process keeps on running until completion. Okay. The advantages of this scheduling policy is it's simple, and there is minimal context switch overhead. Like we do context switch only when it is absolutely necessary. That means when the process terminates or the process itself yields the CPU or the process is blocked. Okay. When we know that the process has nothing to do, that's when the scheduling happens. Note that this is non-preemptive. That means we never forcefully snatch the CPU away from the process. Rather, we take the CPU only when the process doesn't need it. Okay. What's the disadvantage of this scheduling policy? One simple disadvantage is it has short response time, right? Imagine if there are three processes, and if one process keeps on running and the third process has to wait till the first two processes finish. So the response time for the third process suffers. Okay, that's one disadvantage. There are various other disadvantages with this policy as well. The second policy is round robin. So here, what happens is usually the operating system maintains a list of processes that are ready to be run. It's usually called ready queue. And whenever timer interrupts triggers, so whenever a time slice or quantum of time expires, then operating system will choose the next process in the list and it will schedule that process. Okay. And here, one of the main things to consider is the time slice. That means the amount of time to be given for each process. Because if the time is very less, which actually is good because it improves the response time. However, we will suffer from overhead because now the operating system has to do context switch very frequently. So there are these two conflicting requirements. And usually, what happens is in real operating systems, overhead is typically about 1% of the total uh, time period or total quantum. And quantum is typically between 10 to 100 milliseconds, depending on different operating system configurations. So one thing to note about round robin is actually very fair because every process that is ready to be run on CPU will always get the same time slice, and we go in round robin fashion so that it's fair to all the processes. Is fairness always good? Not necessarily, right? For instance, uh, let's say we have 10 jobs that are waiting to be run, waiting to be scheduled. And let's say each job takes 100 seconds. And let's assume there is no other overhead. So, what's the total CPU time that is needed to execute all the 10 jobs? It's 10 into 100, which is 1000 seconds, always, right? So, it doesn't matter which scheduling policy we use, last job always finishes at 1000th second. Okay. So, last job always finishes at like 1000 second. So, what's the point of scheduling? Now we know that It doesn't matter which order in which we schedule the jobs, the last job will always finish at 1000 seconds. So do we really need to schedule the jobs? Do we really need to schedule, do we really need to switch the processes? Let's look at this in different scenarios. Okay. So let's take the simplest case. We have 10 jobs. So let's take the FIFO example. So FIFO, as we know, it's first come, first out scheduling policy where jobs are run in the order in which they arrive or in the order in which they are ready. So job one starts at time 0, it ends at time 100. Job 2 starts at time 100, ends at time 200, so on and so forth. Finally, job 10 starts at 900 and it ends at 1000. Okay. So average turnaround time, which is the completion time minus the arrival time. So assuming all the jobs arrived at the same time, so the completion time is actually equal to the turnaround time because arrival time is time 0. So the turnaround time for each job is end time minus 0, which is the end time. So average turnaround time is the turnaround time for each job divided by total number of jobs. So turnaround time for job 1 is 100, job 2 is 200, so on and so forth. Then when we divide it by 10, we get 550 seconds. So average turnaround time in case of FIFO for 10 jobs is 550 seconds. Okay. Now let's look at round robin, and let's assume the time slice or the quantum is 1 second. So here job 0 executes at second 0, and then context which happens, and second 1 it's the job 1 that gets run, and the second 2 it's the job 2, so on and so forth. And then after second 9 at which job 10 execute, job 9 runs, then we go back from job 0, job 1, job 2. So you can see that we are assigning 1 second to each job in a round robin fashion. Okay. So here the completion time is as shown on the end. So here average turnaround time, if you see, it's 995. It's actually way more than FIFO. Okay. So in FIFO, it's actually 550 seconds, whereas in case of round robin, it's 995 seconds. This is surprising, right? Because round robin is actually fair. And but given the scenario, it seems counterintuitive that actually the unfair policy, which is the first in first out scheduling policy, is actually faster. That means like average turnaround time is less. And this because job 10 always ended at the same time. So round robin just hurt like all the jobs from 1 to 9 without getting any gain whatsoever. It actually made the system worse when the system was better if we had used first come first serve scheduling policy, right? But let's take, of course, in that scenario, this is true. Let's take a different scenario. Okay. Let's take the same 10 jobs. However, here in this case, job 10 takes only 10 seconds. So in our earlier scenario, all the jobs took 100 seconds, whereas in the present scenario, jobs 1 to 9, they take 100 seconds, whereas job 10 takes only 10 seconds. Which policy do you think is better now? Let's see. So let's start with FIFO. As we know, job 1 to 9, they take 100 seconds each, and job 10 takes only 10 seconds. So in case of FIFO, we start by executing job 0 to job 10 in that order. Here, as we know, if you see the job 10 ends at 9:10 because it takes only 10 seconds and it starts at 900. So average turnaround time is 541. It decreased, but a bit. Okay. Now let's look at round robin. So in case of round robin, the average turnaround time actually decreased quite a lot. It's 824. So the total work or like the total CPU time needed dropped by 9% when we reduced because job 10 now takes only 10 seconds. So 9% of work drop resulted in only 2% turnaround drop for FIFO, whereas in case of round robin, average turnaround time dropped by 17%. Okay, so when we have, so this thing should actually give us an hint when there are like smaller jobs or jobs that take less time. It seems to be that a round robin is gaining a lot when we have jobs, like when we have small jobs or rather jobs that take less time. Okay. Let's take another example. Let's take the extreme case where only one job takes, like job one takes 100 seconds, whereas job 2 to 10 takes only 10 seconds each. Here, if you do the if you do the calculation, you see that in case of FIFO, the average turnaround time is 145, whereas in case of round robin, the average turnaround time is only 105. So this shows that when we have like smaller jobs or jobs that take less time, round robin is actually has low turnaround time. And this is interesting to see, like, because the policy that we want to choose depends on the jobs that we have currently in the system. So, however, like we just looked at FIFO, but there is a better thing that we can do when we know all the jobs, right? Let's say we only want to improve average turnaround time. FIFO, what happens is, let's consider three jobs, C, A, B. And so here, in case of FIFO, we start by executing C because that arrived first, and then A and then B, okay? Because based on their arrival. Consider another scheduling policy, which we call shortest job first or shortest time to completion first. In this scheduling policy, what happens is we pick the job that has the shortest time. Okay, so that means here when C, A, B arrived, we at time T1, when we have to schedule the jobs, we pick the job that has the lowest time. Here the job with the shortest completion time, or like the lowest time, is A. So we start by executing A, and then we wait until A finishes, and then we pick the shortest job again, which is now B. So we execute B, and then finally we we execute C. So shortest job actually is better than FIFO when we want to optimize for turnaround time. So actually, we can theoretically prove that if we use shortest job first scheduling policy, then it will give us minimal average turnaround time. However, here the assumption is we should know that we should know all the jobs should arrive at the same time. So that's a huge assumption. So given a configuration of a system, basically if all the jobs arrive at very same time, then shortest job first is the best policy, is the policy that will give the minimal, or like rather minimum, average turnaround time. Okay. However, one obvious disadvantages of this policy is we cannot predict the future, right? We cannot know, we cannot assure that all the jobs arrive at the same time. Jobs can arrive at different times, so user may want to execute certain jobs later or after some time. So although this policy has a very nice theoretical guarantee that it provides the least uh, average turnaround time, but it has one major disadvantage, that all the jobs should arrive at the same time, or like rather at the beginning, so which is very hard to achieve on real systems. So so let's say the in case of shortest job first and FIFO, we considered a non-preemptive policy, right? Those are non-preemptive scheduling policy. That means the processes, when once they start running, the CPU is never snatched away from them. Okay. So let's consider preemptive scheduling policy. Okay. Here, we can, when we, let's say if we can preempt the policy, so instead of using shortest job first, we can actually use shortest remaining time to completion first. So here it's a preemptive scheduling policy. So that means we actually stop the running process, rather pause the running process, and pick another active process and schedule the process again. Okay. So here, what happens is, so in case of shortest remaining time to completion, so the jobs at any time, the job which has the shortest time will be executing on the CPU. Okay. So the example is shown on the second half of the slides of the slide, right? So here, let's say C arrives, okay, and operating system starts scheduling C because that's the only job. And let's say when A arrives, when process A arrives, now the process that has the shortest time is A. So A starts executing until it finishes. And then once A finishes, again only C is remaining. So C continues execution. Let's say B arrives. So when B arrives, now the job with shortest time is B. So B takes away the CPU and B starts executing until completion. And then finally, C finishes to completion. So here, as you can see, depending on the configuration of the system, depending on which process has the shortest time, that process will be executed on the CPU. This actually ensures, like, this is a preemptive scheduling policy where, like, if we can preempt the processes, then actually shortest remaining time to completion actually gives us minimal turnaround time. So whereas shortest job to completion gives us minimal when we cannot preempt, whereas if we can preempt, then shortest remaining time to completion gives us the minimal average turnaround time. However, you can imagine like one obvious problem with the shortest remaining time completion, right? It can lead to starvation. That means, imagine if there is a long running job, then the arrival of short running jobs could actually starve the long running job, because long running job may never get to run because short running jobs will always be running on the CPU. So, what are our observations so far from the four scheduling policies that we have seen? So, we need some way to accommodate interactive jobs. So, we need some kind of round robin scheduling. And we also have diversity of the jobs, because jobs can have different runtime. Like there could be smaller jobs, there could be larger jobs, or like long running jobs. So, here round robin also seems to help here a bit, because like when we have like round robin ensures that every job gets some time slice, so it also helps there. And shortest job first has a nice guarantee, right? The It has the minimal average turnaround time. So shortest job first actually has a very nice and strong guarantee. It actually ensures something. So finally, depending on various properties of, like we saw that there are various properties that each scheduling policy has, can we accommodate all of them? Can we have a policy, or rather can we design a policy that has all the good things of different policies? So yeah, like to summarize, we have FIFO that has highest throughput, because we never operating system never uses a CPU for anything apart from running running the jobs. Okay, because the scheduling happens only when the user process doesn't need the CPU. Okay, it has high throughput. On the other hand, round robin has good response time, it has decent turnaround time, and it's actually very fair. Okay, and shortest job first has a very nice guarantee that it provides minimal average turnaround time. Okay, so, and just to reiterate, like, a good policy has five goals, like fairness, it should be fair, flexible, and it should have high utilization, like basically throughput should be high. And finally, we should have good response time and turnaround time as well. So high utilization, we saw like scheduling policy, CPU scheduling policy. The utilization is not only for CPU, but there are various other resources on the system where we should consider the utilization as well. For instance, a scheduling policy may utilize CPU very well, but it may not be able to utilize, for instance, other resources like network card well. Okay, so we should also make sure that scheduling policy uses all the system resources in an efficient way. Exactly, right? So we have we have different types of processes with different requirements, which need, that means each processes might need different resources, and we have lots of resources. We have different resources as well. So we want to get, we want to ensure that all the resources are used in an efficient way. That means the throughput, or like the useful work done by the system, should be maximum. So let's consider an example like where we have processes that use resources other than CPU. For instance, let's consider uh, processes with which has input output that needs to be taken care of. Okay, so let's say we have process A and B, each use 100% CPU, and process C, which has an intermixed CPU and disk usage. So CPU just loops forever, where in each loop it uses 1 millisecond of CPU and it needs 10 milliseconds of disk. Okay. So now consider round robin scheduling with time slice of 99 milliseconds. Okay. So here, if you actually plot, if you see the timing diagram of each of the process, you will see that roughly 30% of the disk will be utilized and 70% of the CPU will be utilized. Okay. That means the other 30% of the CPU would be halted, like where, for instance, for instance, process C, it requires, like for instance, let's say process C, right? When it gets scheduled, so it will be scheduled for 99 milliseconds. That means although it needs only 1 millisecond of CPU, 10 milliseconds of disk, so it has 99 milliseconds of CPU time. You can imagine that the other time is just wasted, right? So now let's consider time slice to be 1 millisecond. So here, if you see, if you plot the timing diagram of each ABC, you'll see that 90% of the disk will be utilized, and 100% of, along with 100% of CPU utilization. What this shows is that small time slice can actually improve utilization and fairness when we have jobs with the IO, or like when we have jobs that require resources other than CPU. So in the next class, we will be looking at more CPU scheduling policies, or rather more decisions that involve selecting a good CPU scheduling policy. And we also be looking at threads, which also provide a good abstraction and rather much lightweight abstraction of processes. Thank you.